In the early decades of the 20th century, astronomers believed they understood the essential shape of the cosmos. The universe, they thought, was vast but ultimately knowable. Telescopes could be improved, techniques refined, and given enough time and patience, humanity might one day map the full extent of what existed. There was comfort in this belief. The night sky, though filled with distant points of light, seemed to obey comprehensible rules. Galaxies were scattered through space like islands in a dark sea, and while the distances were staggering, they were finite. The universe had a size, an age, a structure that could be measured and understood. This confidence was not arrogance, but rather the product of careful observation and mathematical reasoning. Scientists had discovered that the universe was expanding, that galaxies were moving away from one another, and that tracing this motion backward suggested a beginning, a moment when everything emerged from a state of unimaginable density and heat. This origin point, later called the Big Bang, occurred roughly 13.8 billion years ago, and from that anchor in time, the rest of the cosmic story could be told. Stars formed, galaxies assembled, elements were forged in stellar furnaces, and eventually, in quiet corners of the universe, conditions arose that allowed for complexity, chemistry, and life. It was a narrative that felt complete, even if many details remained unknown. But this sense of completeness rested on an assumption that what we could see represented most of what existed. Early telescopes captured visible light, the same wavelengths that human eyes detect, and the universe they revealed was impressive but constrained. Deep surveys of the sky, painstakingly assembled over decades, cataloged millions of galaxies, and astronomers used these catalogs to estimate the total population of galaxies in the observable universe. The numbers were already staggering: hundreds of billions of galaxies, each containing hundreds of billions of stars, but the estimates carried an implicit boundary. Beyond a certain distance, galaxies faded from view, their light too faint to register on photographic plates or electronic sensors. This fading was understood as a natural limit, a consequence of distance and the inverse square law of light propagation. The farthest galaxies known in the late 20th century existed at distances corresponding to light travel times of several billion years, meaning that the light captured by telescopes had been journeying through space for billions of years before arriving at Earth. These galaxies were seen not as they are now, but as they were in the distant past, their images frozen at a moment long before the Sun or Earth existed. Astronomers accepted this temporal displacement as an unavoidable feature of observation. Looking out into space necessarily meant looking back in time, and the night sky was not a snapshot of the present, but an archive of history, layered by distance and age. Yet even as this understanding deepened, there remained a persistent assumption that the darkness between galaxies was truly empty. Where no light was detected, it was believed that no galaxies existed, or at least none bright enough to matter. This assumption was reasonable given the limitations of the instruments available. Visible light telescopes, no matter how large or sensitive, could only capture what their detectors were designed to see. And what they were designed to see was a narrow band of the electromagnetic spectrum, the wavelengths that happened to be abundant in the light emitted by stars and galaxies relatively close to us in cosmic time. But light changes as it travels through an expanding universe. The expansion of space itself stretches the wavelengths of photons, shifting them toward the red end of the spectrum, a phenomenon known as redshift. For galaxies at moderate distances, this redshift is modest, and their light remains visible to optical telescopes. But for galaxies at truly immense distances, galaxies that existed when the universe was very young, the redshift becomes extreme. The light they emitted as ultraviolet or visible radiation is stretched so much by the time it reaches us that it arrives as infrared, wavelengths invisible to the human eye and to most traditional telescopes. These ancient galaxies were always there, scattered throughout the early universe, but they were invisible, hidden not by darkness, but by a transformation of their light that rendered them undetectable to the instruments astronomers have been using for more than a century. This invisibility was not understood as a fundamental barrier for long. By the late 20th century, astronomers recognized that to see the earliest galaxies, they would need telescopes designed to observe in the infrared. The Hubble Space Telescope, launched in 1990, carried instruments capable of detecting some infrared light, and over its decades of operation, Hubble pushed the boundaries of observation deeper into space and further back in time. Its deep field images, assembled by pointing the telescope at a seemingly empty patch of sky and collecting light for days, revealed thousands of faint galaxies where none had been visible before. Each of these galaxies was a distant beacon, its light having traveled for billions of years, and the deeper Hubble looked, the younger the galaxies it found. Some of the farthest galaxies detected by Hubble existed less than 1 billion years after the Big Bang. Their light redshifted so much that only Hubble's infrared instruments could capture them. These discoveries were profound. They showed that galaxies had formed much earlier than many models predicted, and they hinted at a universe far more densely populated with young galaxies than previously imagined. But Hubble had limits. Its infrared capabilities, while groundbreaking, were not its primary strength, and the faintest, most distant galaxies remained just beyond its reach, detectable only as faint smudges or not at all. Astronomers knew that to truly see the early universe, to capture the light from the first generations of galaxies, they would need a telescope designed specifically for infrared observation, a telescope larger, colder, and more sensitive than anything that had come before. The James Webb Space Telescope was conceived as that instrument. Its development spanned decades, involving thousands of scientists, engineers, and technicians from multiple countries, and its design reflected a singular purpose: to observe a universe in the infrared with unprecedented clarity and sensitivity. Webb's primary mirror, composed of 18 hexagonal segments coated in gold to enhance infrared reflection, measures 6.5 meters across, making it significantly larger than Hubble's 2.4-meter mirror. This size is critical because the amount of light a telescope can collect depends on the area of its mirror, and more light means the ability to see fainter, more distant objects. But size alone is not enough. Infrared observation requires extreme cold. Infrared radiation is essentially heat, and any warm object emits infrared light, which can overwhelm the faint signals from distant galaxies. To avoid this, Webb's instruments are cooled to temperatures just a few degrees above absolute zero, and the entire telescope is shielded by a massive sun shield, a structure roughly the size of a tennis court, composed of 5 layers of thin material designed to block the heat from the sun, Earth, and Moon. This sun shield allows Webb's instruments to remain cold enough to detect the faint infrared glow of galaxies billions of light years away. To maintain this cold environment, Webb orbits not around Earth, as Hubble does, but at a point in space called the second Lagrange point, or L2, roughly 1.5 million kilometers from Earth in the direction opposite the Sun. At L2, the gravitational forces of the Sun and Earth balance in such a way that Webb can maintain a stable position relative to Earth, while keeping its sun shield between itself and the Sun at all times. This distant orbit also places Webb far from the thermal glow of Earth, further reducing unwanted infrared noise. The telescope was launched on December 25, 2021, and after a month-long journey to L2, during which its mirror and sun shield were carefully unfolded and deployed, it began a period of calibration and testing. The first science images were released in July 2022, and they immediately revealed a universe more intricate and populated than expected. One of the earliest images, known as Webb's first deep field, captured a small region of sky and revealed thousands of galaxies, many of them so distant that their light had been traveling for more than 13 billion years. The image was astonishing not only for its clarity, but for the sheer number of galaxies visible in such a tiny patch of sky. If the entire sky were surveyed at this depth, the total number of galaxies in the observable universe would be far higher than previous estimates suggested. But the most striking aspect of Webb's early observations was not just the quantity of galaxies, but their nature. Among the galaxies detected were some that existed only a few 100 million years after the Big Bang, galaxies that formed when the universe was less than 3% of its current age. These galaxies were not the small, dim, chaotic collections of stars that many models predicted. Instead, they were bright, massive, and surprisingly well-organized, with structures that resembled those of much older galaxies. Some contained as much mass and stars as galaxies that formed billions of years later, and their brightness suggested high rates of star formation, far exceeding what standard models of galaxy evolution could easily explain. This unexpected brightness and mass presented a challenge. According to the prevailing understanding of galaxy formation, galaxies grow gradually over time through the accumulation of gas and the formation of stars, as well as through mergers with other galaxies. In the early universe, when the first galaxies were forming, the available time was very limited. A galaxy observed as it was 400 million years after the Big Bang had only 400 million years to assemble its stars and structure. Given the slow processes of gas cooling, star formation, and gravitational assembly, models predicted that early galaxies should be small and faint, with relatively few stars. Yet Webb was finding galaxies that appeared to have assembled their stellar populations far more quickly than anticipated. Some contained hundreds of millions or even billions of solar masses worth of stars, and their light was bright enough to be detected across the vast distance of space and time. This discrepancy between observation and prediction became known informally as the too much light too early problem, though the phrase is somewhat misleading. The issue is not that the light itself is anomalous, but that the galaxies producing it seem to have formed stars at rates and efficiencies that challenge the timelines allowed by standard cosmological models. One possible explanation is that the initial conditions in the early universe were more conducive to rapid star formation than previously thought. Perhaps the gas in early galaxies was denser or cooled more efficiently, allowing stars to form faster. Another possibility is that the stellar populations in these early galaxies were unusual, dominated by massive stars that burned brightly but briefly, producing more light per unit mass than typical stellar populations. Alternatively, some astronomers have suggested that what appears to be a large mass of stars might include contributions from other luminous sources, such as active galactic nuclei, where supermassive black holes accreting matter produce enormous amounts of light. The mention of supermassive black holes introduces another layer of complexity to the picture Webb has revealed. At the centers of most large galaxies, including our own Milky Way, there exists a supermassive black hole, an object with a mass millions or billions of times that of the Sun, concentrated in a region smaller than our solar system. How these black holes form and grow is not fully understood, but the prevailing view has been that they start as smaller black holes, perhaps remnants of the first massive stars, and grow over billions of years by accreting gas and merging with other black holes. This gradual growth process implies that supermassive black holes should be relatively rare and modest in mass in the early universe. Yet Webb has detected signatures of supermassive black holes in galaxies that existed less than 1 billion years after the Big Bang, and some of these black holes have masses comparable to those found in much older galaxies. The presence of such massive black holes so early in cosmic history is difficult to reconcile with standard growth models. If black holes start small and grow by accreting matter, there simply may not have been enough time for them to reach such large masses so soon after the Big Bang. This has prompted speculation about alternative formation mechanisms. Perhaps some black holes did not form from stars but instead collapsed directly from dense regions of gas in the early universe, starting with much larger initial masses. Or perhaps the conditions in the early universe allowed for more efficient accretion, with black holes growing faster than current models predict. These possibilities remain speculative, and the data from Webb are still being analyzed, but the mere presence of these massive black holes in the early universe suggests that something about the standard timeline of cosmic structure formation may need revision. As Webb continued its observations, it became clear that the early universe was not only more active than expected, but also more densely populated. Surveys of deep fields, regions of sky observed for extended periods to capture the faintest possible light, revealed galaxies at nearly every distance and every epoch. Wherever Webb pointed, if it looked long enough, it found galaxies. This ubiquity has implications for the total number of galaxies in the observable universe. Earlier estimates, based on Hubble observations and extrapolations from shallower surveys, suggested that the observable universe contains somewhere between 100 billion and 200 billion galaxies. But Webb's ability to detect faint, distant, and highly redshifted galaxies has pushed those numbers higher. Some astronomers now estimate that the total number of galaxies in the observable universe could be closer to 2 trillion. And this number may still be an underestimate, as even Webb cannot detect every galaxy, particularly those that are small, faint, or obscure by dust. The realization that the universe contains trillions of galaxies, each with billions or hundreds of billions of stars, is humbling. It suggests that the night sky, even in its darkest regions, is not empty but filled with light that has not yet been captured. Light from galaxies so distant or so faint that they remain invisible even to our most powerful instruments. Yet the distribution of these galaxies is not random. Observations over the past several decades have revealed that galaxies are not scattered uniformly through space, but are organized into a vast structure known as the cosmic web. This web consists of filaments, dense threads of galaxies and dark matter that stretch across hundreds of millions of light years, connected at intersections called nodes or clusters, which are regions of particularly high galaxy density. Between these filaments lie voids, enormous empty regions where galaxies are rare or absent. The cosmic web is a natural consequence of the way matter clumps under the influence of gravity. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny fluctuations in density. But gravity amplified these fluctuations over time. Regions that were slightly denser than average attracted more matter, growing denser still, while regions that were slightly less dense lost matter and became emptier. This process, acting over billions of years, produced the large-scale structure observed today. Galaxies form where matter is densest, along the filaments and in the clusters, and they are largely absent from voids. The cosmic web is both a map of where galaxies are and a record of how gravity shaped the distribution of matter over cosmic time. Webb's observations have not fundamentally changed this picture, but they have filled in details and extended the web's history further back in time. Early filaments and protoclusters, the precursors to today's cosmic web, are now visible in Webb's deep fields, showing that the process of structure formation began very early in the universe's history. Some of the galaxies Webb detects are located along filaments that existed when the universe was less than 1 billion years old, suggesting that the cosmic web began to take shape much sooner than some models predicted. This early emergence of structure is consistent with the idea that dark matter, the invisible substance that makes up most of the universe's mass, played a crucial role in seeding galaxy formation. Dark matter does not emit, absorb, or reflect light, so it cannot be observed directly, but its presence is inferred from its gravitational effects. Galaxies rotate in ways that suggest they contain far more mass than can be accounted for by stars, gas, and dust. Clusters of galaxies are held together by gravitational forces that require far more mass than is visible. And the large-scale structure of the cosmic web, with its filaments and voids, matches predictions from simulations that include dark matter, but not simulations that rely on visible matter alone. Dark matter, it seems, forms the invisible skeleton of the cosmic web. With ordinary matter, the atoms and molecules that make up stars, planets, and people, tracing out the structure defined by dark matter's gravitational pull. Recent observations from Webb and other telescopes have provided new evidence for dark matter's role in the cosmic web. Gravitational lensing, the bending of light by gravity, allows astronomers to map the distribution of mass in the universe, including dark matter. When light from a distant galaxy passes through a region of space containing a large concentration of mass, such as a galaxy cluster or a filament, the mass bends the light's path, distorting the galaxy's image. By analyzing these distortions, astronomers can infer the distribution of mass, both visible and dark. Webb's high-resolution imaging has enabled detailed lensing studies, and these studies have detected dark matter not only in clusters but also along filaments, confirming that dark matter forms the connective tissue of the cosmic web. Some of the most intriguing lensing observations involve filaments between clusters, where dark matter appears to flow along the same paths traced by galaxies, though the dark matter outweighs the visible matter by factors of several to one. This discovery reinforces the view that what we see, the galaxies and their light, is only a small fraction of what exists. The universe is dominated by dark matter, a substance that we cannot observe directly, and by dark energy, an even more mysterious component that we will turn to shortly. The concept of the observable universe is central to understanding what Webb can and cannot reveal. The observable universe is defined as the region of space from which light has had time to reach us since the Big Bang. Given that the universe is roughly 13.8 billion years old, one might expect that the observable universe extends roughly 13.8 billion light-years in all directions, giving it a diameter of about 27.6 billion light-years. But this calculation ignores the expansion of space. Space itself has been expanding since the Big Bang, and the rate of expansion has varied over time. In the early universe, space expanded very rapidly, and even today, space continues to expand, carrying galaxies farther apart. This expansion means that a galaxy whose light has taken 13.8 billion years to reach us is not currently located 13.8 billion light-years away. During the time the light was traveling, the space between us and that galaxy was expanding, stretching the distance. When accounting for this expansion, the current distance to the farthest observable galaxies is roughly 46.5 billion light-years, making the diameter of the observable universe approximately 93 billion light-years. This distance defines the cosmic horizon, the boundary beyond which light has not had time to reach us. Galaxies beyond this horizon exist, but their light has not yet arrived, and given the expansion of space, some of their light may never arrive. The cosmic horizon is not a physical edge. Space does not end at the horizon. Instead, the horizon represents a limit of observation, a boundary defined by light travel time and the expansion of space. Beyond the horizon, the universe continues, extending perhaps infinitely, but we have no way to observe it directly. This raises a subtle but profound point. The observable universe is not the entire universe. It is only the portion of the universe that is accessible to observation from our particular location in space and time. An observer in a different galaxy, especially one very far away, would have a different observable universe, centered on their location, overlapping with ours in some regions, but extending into regions we cannot see and missing regions that we can. In this sense, every observer has their own cosmic horizon, their own observable universe, and there exist galaxies that are visible to us, but not to some distant observers, just as there are galaxies visible to them, but not to us. And there are galaxies that lie beyond the horizon of all observers, galaxies whose light has not yet reached anyone because the universe is not old enough and space is expanding too quickly. This brings us to one of the most unsettling discoveries of modern cosmology, the existence and nature of dark energy. In the late 1990s, astronomers studying distant supernovae, exploding stars that could be used as standard candles to measure cosmic distances, made an unexpected discovery. They found that the expansion of the universe is not slowing down, as had been assumed, but is instead accelerating. Galaxies are not only moving away from us, they're moving away faster and faster over time. This acceleration cannot be explained by gravity, which pulls matter together and should slow the expansion. Instead, it suggests the presence of a new component of the universe, something that exerts a kind of repulsive force, driving space to expand ever more rapidly. This component was named dark energy, and it has become clear that it dominates the universe. While ordinary matter, the atoms that make up stars, planets, and gas, accounts for only about 5% of the universe's total energy content, and dark matter account for about 27%. Dark energy accounts for roughly 68%. Dark energy is the largest component of the universe, yet its nature remains entirely unknown. It does not clump like matter. It does not emit, absorb, or interact with light. Its only known effect is to drive the accelerated expansion of space. The existence of dark energy has profound implications for the long-term visibility of the universe. Because space is expanding at an accelerating rate, galaxies that are currently observable will eventually move beyond the cosmic horizon. As space stretches, the light from these galaxies will be redshifted to ever longer wavelengths, becoming fainter and eventually undetectable. Over billions of years, the number of galaxies visible from any given location in the universe will decrease. Galaxies that are currently on the edge of our observable universe will slip beyond the horizon, their light stretched into invisibility. Eventually, in the far future, observers in our galaxy, or in whatever structure our galaxy becomes part of after merging with neighbors like Andromeda, will look out and see only the galaxies in their local group, the small cluster of galaxies gravitationally bound together. All other galaxies will have receded beyond the horizon, and the universe will appear nearly empty. The cosmic web, with its filaments and clusters, will be invisible, not because it ceased to exist, but because its light can no longer reach observers. This future isolation is a consequence of dark energy. It means that the universe we currently observe, rich with galaxies and structure, is in some sense a temporary view. Most of the universe is already beyond our reach, and as time goes on, even more of it will become inaccessible. Webb's observations have not changed the fundamental nature of dark energy, but they have contributed to a related puzzle known as the Hubble tension. The Hubble constant is a number that describes the current rate of expansion of the universe. It can be measured in two primary ways. One method uses observations of the cosmic microwave background, the faint glow of radiation left over from the Big Bang, which encodes information about the early universe. By analyzing the patterns in this radiation, astronomers can infer the expansion rate at that early time and extrapolate forward to the present using models of how the universe evolved. This method yields a Hubble constant of about 67 kilometers per second per megaparsec. The other method uses observations of relatively nearby objects, such as Cepheid variable stars and supernovae, whose distances and velocities can be measured directly. These local measurements consistently yield a higher value, around 73 kilometers per second per megaparsec. The discrepancy between these two measurements is the Hubble tension. It is not a small difference. The gap is too large to be explained by measurement uncertainty, and it has persisted despite increasingly precise observations. Webb has contributed to this tension by providing new, high-resolution measurements of Cepheid variables and other distance indicators, confirming the higher local value. The tension suggests that something about our understanding of the universe's expansion is incomplete. Perhaps dark energy behaves differently at different times or in different regions. Perhaps there is additional physics affecting the expansion rate that current models do not account for. Or perhaps the assumptions underlying one or both measurement methods are flawed in ways that are not yet understood. The tension remains unresolved, and it is one of the most active areas of research in cosmology. Throughout all of these observations, a theme emerges. The universe is larger, older, more complex, and more inaccessible than we once imagined. Webb has not revealed the edge of the universe because the universe, as far as we can tell, has no edge. Instead, Webb has revealed the edge of what can be known, the boundary imposed not by the universe itself, but by the speed of light and the expansion of space. The observable universe is a bubble of information, a region within which signals can reach us, but it is not the whole of reality. Most of the universe lies beyond the cosmic horizon, existing but unobservable, and as dark energy drives accelerated expansion, even some of what we can see now will eventually slip beyond reach. This realization is both humbling and profound. It means that no matter how powerful our telescopes become, no matter how long we observe, there will always be regions of the universe that remain forever unknown to us. These regions exist in the same sense that observable regions do. They contain galaxies, stars, perhaps planets and life, but they are causally disconnected from us. No signal from them can reach us, and no signal we send can reach them. They are part of the universe, but they are not part of our universe, if by our universe we mean the totality of what we can ever observe or influence. The implications extend beyond astronomy. If most of the universe is unobservable, then most of reality is beyond the reach of science, at least as science is traditionally understood as a process of observation, hypothesis, and testing. We cannot test hypotheses about regions of space we cannot observe. We cannot confirm or refute theories about galaxies whose light will never reach us. This does not mean that science is futile, but it does impose a kind of epistemic humility. There are limits to what we can know, not because of technological constraints that might one day be overcome, but because of fundamental features of the universe itself. The speed of light is finite, the universe is expanding, and these facts together impose a horizon. We live inside an informational bubble, and while we can study that bubble with ever-increasing precision, we cannot step outside it. The universe is indifferent to our desire to understand it. It unfolds according to physical laws, and those laws include boundaries on observation. Yet within the observable universe, Webb has dramatically expanded what we can see and understand. Its infrared vision has revealed galaxies that were invisible to previous generations of telescopes. It has shown that the early universe was already rich with structure and activity, that galaxies formed faster and black holes grew larger than models predicted, and that the processes shaping cosmic evolution were more efficient and complex than anticipated. These discoveries have not provided final answers. Instead, they have generated new questions, refined old puzzles, and challenged assumptions that seem secure. This is the nature of progress in science. Each new capability, each new telescope, each new dataset does not close the book on a subject, but instead opens new chapters, revealing deeper layers of complexity. Webb is not the final word on the universe. It is a tool, an instrument of extraordinary capability, but still limited by the laws of physics and the constraints of observation. Future telescopes, perhaps located on the far side of the moon or in deep space, may extend our view even further, detecting galaxies at even greater distances or observing wavelengths that Webb cannot access. But no telescope, no matter how advanced, will allow us to see beyond the cosmic horizon. That boundary is fundamental, a consequence of the finite speed of light and the expansion of space, and it will always define the limits of the observable universe. The structure of the cosmic web, revealed in ever greater detail by Webb and other observatories, provides a kind of map of the observable universe. The filaments, clusters, and voids form a pattern that is both beautiful and informative. The pattern reflects the initial distribution of matter in the early universe, amplified by billions of years of gravitational evolution. It shows how small fluctuations in density grew into galaxies and clusters, how matter flowed along paths defined by gravity, and how empty regions emerged where matter was scarce. The cosmic web is not static. It continues to evolve, with galaxies merging, clusters growing, and filaments extending. But the overall pattern, the large-scale structure, is already in place, and it will remain recognizable for billions of years, even as dark energy drives accelerated expansion and eventually begins to stretch the web apart. In the far future, the cosmic web will dissolve. The filaments will thin, the clusters will disperse, and galaxies will become isolated, separated by ever-increasing distances. But that future is distant, and for now, the web remains, a vast architecture of matter and light, stretching across the observable universe. One of the striking aspects of Webb's observations is the realization that the darkness we perceive in the night sky is not true darkness. It is filled with light, but light that is too faint, too redshifted or at wavelengths we cannot see without instruments. If human eyes were sensitive to infrared, the night sky would appear vastly different. Regions that seem empty would glow with the light of distant galaxies. Their infrared radiation stretched from the ultraviolet and visible light they emitted billions of years ago. The sky would be crowded, filled with faint smudges and points of light, each representing a galaxy at some distance and some point in cosmic history. This invisible light has always been there, raining down on Earth, passing through us, ignored because it falls outside the narrow band of wavelengths our eyes can detect. Webb's infrared detectors capture this light, translating it into images and data that reveal the hidden population of galaxies. In doing so, Webb does not create new galaxies but uncovers those that were always present, rendering visible what was previously invisible. The concept of redshift is central to understanding what Webb observes. Redshift is a measure of how much the wavelength of light has been stretched by the expansion of space. Light emitted by a distant galaxy, as ultraviolet or blue, may arrive at Earth shifted into the red or infrared, depending on how far the galaxy is and how much space has expanded during the light's journey. Redshift is often denoted by the symbol Z, with higher values indicating greater distances and earlier times. A redshift of Z equals 1 corresponds to a distance where light has been traveling for about 8 billion years, and the universe was roughly half its current size when the light was emitted. A redshift of Z equals 2 corresponds to a light travel time of about 10 billion years, with the universe about a third its current size. As redshift increases, the look-back time grows, and the universe becomes younger and smaller in the observed epoch. Webb has detected galaxies with redshifts as high as Z equals 13 or more, corresponding to a time when the universe was only a few hundred million years old. At these extreme redshifts, the light that was emitted as ultraviolet arrives at Earth as infrared, shifted across the entire visible spectrum and beyond. This is why infrared telescopes are essential for studying the early universe. Visible light telescopes cannot detect these galaxies because their light is no longer in the visible range by the time it reaches us. The process of observing such distant galaxies is painstaking. Webb's deep field observations require long exposures, sometimes dozens or even hundreds of hours, during which the telescope remains pointed at a small patch of sky, collecting photons one by one. Each photon that reaches Webb's detectors has traveled for billions of years, crossing a significant fraction of the observable universe before finally being captured. The journey of these photons is not straightforward. They pass through regions of expanding space, around galaxies and clusters whose gravity bends their paths slightly, through clouds of gas and dust that may absorb or scatter some photons, and across vast stretches of empty space where nothing impedes them. The photons that survive this journey and happen to arrive at Webb's position in space and time are an infinitesimal fraction of the photons emitted by the distant galaxy. Most photons emitted by any galaxy travel in other directions, never encountering Earth or any observer. Of those that do travel in our direction, many are absorbed or scattered before reaching us. The photons that Webb detects are survivors, carriers of information about a galaxy that existed billions of years ago, and their arrival allows us to reconstruct what that galaxy looked like, how massive it was, how fast it was forming stars, and what elements it contained. The elements themselves provide another layer of information. The first stars that formed in the universe were composed almost entirely of hydrogen and helium, the only elements created in significant quantities during the Big Bang. These primordial stars, sometimes called population 3 stars, lived fast and died young, ending their lives in supernova explosions that scattered heavier elements, carbon, oxygen, nitrogen, iron, and others, into the surrounding gas. The next generation of stars formed from this enriched gas, incorporating these heavier elements into their composition. Over time, successive generations of stars continued to enrich the gas with heavier elements, a process known as chemical evolution or cosmic nucleosynthesis. By analyzing the spectra of distant galaxies, astronomers can determine which elements are present and in what abundances. This information reveals the chemical history of the galaxy, how many generations of stars have formed and died, and how efficiently the galaxy has recycled material. Webb's spectroscopic observations have detected signatures of heavy elements in some of the earliest galaxies, indicating that chemical enrichment began very early. Some galaxies observed at redshifts corresponding to only a few 100 million years after the Big Bang already show evidence of carbon, oxygen, and other elements, suggesting that massive stars had already formed, lived, and exploded by that time. This rapid enrichment is consistent with the rapid star formation rates inferred from the brightness of these galaxies, and it supports the idea that the early universe was a dynamic, active place, where processes of star formation and chemical evolution proceeded more quickly than in later epochs. The mass of galaxies is another key observable. By measuring the light emitted by a galaxy and making assumptions about the types of stars it contains, astronomers can estimate the total mass of stars in the galaxy. This is not straightforward because different types of stars emit different amounts of light per unit mass. In a stellar population of a galaxy, the mix of massive, luminous stars and smaller, dimmer stars affects the mass-to-light ratio. Nonetheless, with careful modeling, reasonable estimates can be made. Webb's observations of early galaxies have yielded mass estimates that are surprisingly high. Some galaxies observed at redshifts greater than 10 have estimated stellar masses of 1 billion solar masses or more, comparable to the mass of large galaxies in the later universe. The presence of such massive galaxies so early in cosmic history is unexpected, because assembling 1 billion solar masses worth of stars in a few 100 million years requires very high star formation rates, sustained over a significant fraction of the available time. If a galaxy forms stars at a rate of 100 solar masses per year, it would take 10 million years to form 1 billion solar masses. This is not impossible, but it requires that star formation began almost immediately after the Big Bang and continued at a high, sustained rate. It also requires that the gas supply, the reservoir of hydrogen and helium from which stars form, was abundant and accessible. These conditions may have been met in some regions of the early universe, particularly in overdense regions where gravity pulled gas together rapidly. But the fact that so many massive galaxies appear at high redshifts suggests that these conditions were more common than models predicted. The role of mergers in galaxy growth adds another dimension. Galaxies do not grow only by forming stars from gas. They also grow by merging with other galaxies. When two galaxies collide, their stars rarely collide directly because the distances between stars are so large, but the gravitational interaction between the galaxies can funnel gas toward the centers, triggering bursts of star formation, and the galaxies eventually merge into a single, larger galaxy. In the current universe, mergers are an important process, shaping the structure and evolution of galaxies. But in the early universe, when galaxies were smaller and closer together, mergers may have been even more frequent. Webb has captured images of some early galaxies that appear to be in the process of merging, their structures distorted by gravitational interactions. These mergers may have contributed to the rapid assembly of massive galaxies in the early universe, allowing stellar mass to be accumulated not only through star formation, but also through the combination of smaller galaxies. However, even accounting for mergers, the total mass of stars observed in early galaxies remains higher than many models predict, suggesting that both star formation and mergers were more efficient in the early universe than in later times. The brightness of early galaxies is also puzzling from the standpoint of dust. Dust, composed of small particles of solid material, carbon, silicates, metals, forms in the atmospheres of stars and is expelled into the interstellar medium by stellar winds and supernovae. Dust absorbs and scatters light, particularly at shorter wavelengths, causing galaxies to appear dimmer in ultraviolet and visible light and re-emitting the absorbed energy as infrared radiation. In the local universe, dusty galaxies are common, and their presence is taken into account when estimating star formation rates and other properties. But in the early universe, dust should be rare because dust is formed from heavy elements, and heavy elements take time to be produced in stars. The first galaxies, composed of stars made from primordial hydrogen and helium, should have little or no dust. As stars die and enrich the gas with heavy elements, dust begins to form, but this process takes time. Therefore, early galaxies are expected to be relatively dust-free, and their light should be bright at all wavelengths. Yet some of the early galaxies observed by Webb show evidence of dust, with their spectra indicating absorption or emission consistent with dust grains. This suggests that either dust formed more quickly in the early universe than expected, perhaps because massive stars produced and expelled heavy elements rapidly, or that some other process is at work. The presence of dust in early galaxies is not necessarily a contradiction, but it is another surprise, another indication that the early universe was more complex and evolved than simple models suggest. Supermassive black holes at the centers of galaxies present a similar puzzle. As mentioned earlier, these black holes are thought to grow over time by accreting gas and merging with other black holes. But the timescales for growth impose limits on how massive a black hole can become in a given amount of time. There is a maximum rate at which a black hole can accrete matter, known as the Eddington limit, which is determined by the balance between the inward pull of gravity and the outward pressure of radiation from the hot gas falling into the black hole. Accreting at the Eddington limit, a black hole can roughly double its mass every few tens of millions of years. Starting from a seed black hole of a few tens or hundreds of solar masses, the remnant of a massive star, it would take hundreds of millions of years to grow to 1 million solar masses and nearly 1 billion years to reach 1 billion solar masses. But Webb and other observatories have detected active galactic nuclei, the bright emissions from gas accreting on supermassive black holes, in galaxies at redshifts corresponding to less than 1 billion years after the Big Bang. And some of these black holes have estimated masses of hundreds of millions or even billions of solar masses. If these mass estimates are correct, and if the black holes grew by accreting at the Eddington limit, then they must have started from much more massive seeds than stellar remnants can provide. This has led to theories of direct collapse black holes, where regions of dense gas in the early universe collapsed directly into black holes without forming stars first, or of super Eddington accretion, where black holes grew faster than the Eddington limit allows, perhaps because the conditions in the early universe were unusual in ways that are not yet understood. These theories are speculative, and more data are needed to test them, but the presence of massive black holes in the early universe is a robust observational result that demands explanation. The distribution of galaxies across cosmic time provides insight into how the universe evolved. By counting galaxies at different redshifts, astronomers can construct a history of galaxy formation, showing when galaxies were most abundant and when they were forming stars most rapidly. Webb's deep surveys have extended this history to earlier times than ever before. The data show that the number of galaxies per unit volume was lower in the early universe than it is today, which makes sense because galaxies had not yet formed in many regions. But the data also show that the rate of galaxy formation was high in the early universe, with many new galaxies appearing as gas collapsed into dark matter halos and began forming stars. The peak of star formation in the universe occurred roughly 10 to 11 billion years ago, a few billion years after the Big Bang, when the universe was about 20 to 30% of its current age. During this epoch, known as cosmic noon, galaxies were forming stars at the highest rates, and the universe was, in a sense, at its most vibrant. Since then, the overall rate of star formation has declined, as much of the available gas has been consumed or dispersed, and as dark energy has begun to dominate the expansion of the universe, stretching space and making it harder for gas to collapse into galaxies. Today, star formation continues, but at a much lower rate than during cosmic noon. In the far future, as gas becomes even more scarce, and as galaxies become isolated by the expansion of space, star formation will eventually cease, and the universe will enter an era dominated by slowly fading stars and black holes. The timeline of cosmic history, from the Big Bang to the present and beyond, is a narrative of evolution and change. The universe began in a state of extreme density and temperature, a hot, nearly uniform plasma of fundamental particles. As it expanded and cooled, particles combined to form atoms, first hydrogen and helium, and the universe became transparent to light, allowing photons to travel freely for the first time. This moment, about 380,000 years after the Big Bang, is recorded in the cosmic microwave background, the faint glow of radiation that fills the sky at microwave wavelengths. After this recombination epoch, the universe entered a dark age, a period lasting several 100 million years during which no stars had yet formed and the universe was filled with neutral hydrogen gas, dark and cold. The first stars and galaxies formed at the end of this dark age, igniting as gravity pulled gas into dense clumps and nuclear fusion began. These first sources of light reionized the universe, splitting the neutral hydrogen atoms back into protons and electrons, and the universe became transparent again, this time permanently. Webb's observations target this epoch of reionization, capturing the light from the first galaxies as they emerge from the cosmic dark ages. By studying these galaxies, astronomers hope to understand when and how reionization occurred, which types of galaxies contributed most to the ionizing radiation, and how the process unfolded across different regions of space. The reionization epoch is also significant because it represents a phase transition in the state of the universe, from neutral to ionized, from dark to illuminated. This transition had consequences for subsequent galaxy formation, because ionized gas behaves differently than neutral gas under the influence of gravity. Ionized gas is hotter and has higher pressure, making it harder to collapse into galaxies, particularly small galaxies. This may have suppressed the formation of low-mass galaxies during and after reionization, leaving the universe dominated by more massive galaxies that had enough gravitational pull to overcome the increased pressure. Observations of the abundance of small versus large galaxies at high redshifts can test this idea, and Webb's ability to detect faint, low-mass galaxies is critical for these studies. Early results suggest that low-mass galaxies were indeed present during reionization, but their abundance and properties are still being determined. The full picture of reionization, including its timing, sources, and effects on galaxy formation, is one of the major goals of Webb's mission, and the data collected over the coming years will continue to refine our understanding of this critical epoch. As the universe aged beyond the epoch of reionization, galaxy formation continued, but the character of galaxies changed. Early galaxies were often small, irregular, and rich in gas, with high star formation rates and little structure. Over time, as galaxies grew by merging and by accreting gas, they developed more organized structures. Spiral galaxies, with their rotating disks and spiral arms, formed as gas settled into rotating configurations, and elliptical galaxies, with their smooth, featureless distributions of stars, formed from mergers that disrupted the ordered structures of spiral galaxies. The Milky Way, our home galaxy, is a spiral galaxy with a disk of stars, gas, and dust rotating around a central bulge and a supermassive black hole. Its structure is the result of billions of years of evolution, including episodes of star formation, mergers with smaller galaxies, and interactions with neighboring galaxies. Webb's observations of distant galaxies reveal the ancestors of galaxies like the Milky Way, showing what they looked like at earlier stages of their evolution. By comparing early galaxies to local galaxies, astronomers can trace the pathways of galaxy evolution, understanding how different types of galaxies form and how they change over time. The concept of galaxy evolution is intimately tied to the concept of cosmic time. Because the universe is expanding, time and distance are intertwined. A galaxy observed at a high redshift is not only far away in space, but also far back in time. Observing a galaxy at redshift z equals 10 is not like looking at a distant object in the present. It is looking at an object as it was when the universe was only a few % of its current age. This temporal dimension adds depth to observations, turning the sky into a kind of time machine. Every direction we look, we see the universe at a different epoch, with nearby objects representing the recent past and distant objects representing the distant past. The farthest objects visible to Webb correspond to epochs only a few 100 million years after the Big Bang, while the nearest objects correspond to times within the past few million years, practically the present on cosmic timescales. This layering of time means that a single deep-field image captured by Webb contains galaxies from many different epochs, each frozen at the moment when its light began its journey to Earth. By analyzing these galaxies and determining their redshifts, astronomers can arrange them in chronological order, constructing a timeline of galaxy evolution spanning most of the history of the universe. Dark energy's role in this timeline becomes increasingly important in the later epochs. While gravity dominated the early universe, pulling matter together and driving the formation of galaxies and clusters, dark energy has come to dominate in more recent times, driving the accelerated expansion. The transition from gravity domination to dark energy domination occurred roughly 5 to 6 billion years ago, around the time the Sun and Earth were forming. Before this transition, the expansion of the universe was decelerating, slowed by the gravitational attraction of matter. After the transition, the expansion began to accelerate, driven by dark energy. This acceleration has consequences for the future of cosmic structure. While the cosmic web is already in place, and while galaxies within clusters remain gravitationally bound, the clusters themselves are no longer growing by accreting new galaxies. The expansion of space, driven by dark energy, is now faster than the infall of matter into clusters, and so the cosmic web has, in a sense, frozen. The filaments will not extend further, and the voids will not fill in. Instead, the expansion will continue to stretch the web, thinning the filaments and enlarging the voids, until eventually the structure dissolves entirely. But this is a process that will take hundreds of billions of years, far longer than the current age of the universe. The long-term future of a universe, assuming that dark energy remains constant, is a cold, dark, and empty expanse. Star formation will cease as gas is exhausted. Stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Galaxies will dim as their stars fade, and eventually, even the black holes will evaporate through Hawking radiation, a quantum process that causes black holes to lose mass over extremely long timescales. The timescale for a supermassive black hole to evaporate is unimaginably long, far longer than the current age of the universe, but it is finite, and in the extremely distant future, all black holes will disappear, leaving only a diffuse sea of radiation and elementary particles. This endpoint, sometimes called the heat death of a universe, is a state of maximum entropy, where all energy is evenly distributed and no gradients exist to drive any processes. It is a state of ultimate stillness, vastly different from the vibrant, structured universe we observe today. But this future is so distant that it has little relevance to the current or near-term state of the universe. For now, the universe is alive with activity, with stars forming, galaxies merging, black holes accreting, and light traveling across vast distances, carrying information about these processes. Webb's observations contribute to our understanding of this narrative, but they also highlight how much remains unknown. The nature of dark matter and dark energy, which together make up 95% of the universe's content, is still a mystery. The formation and growth of the first supermassive black holes is not fully understood. The processes that drove rapid star formation and chemical enrichment in early galaxies are still being investigated. The full history of reionization, the detailed structure of the cosmic web, and the long-term fate of the universe all remain active areas of research. Each new observation from Webb adds to the body of evidence, refining models and testing theories, but also reveals new puzzles and unexpected phenomena. This is the nature of exploration at the frontiers of knowledge. The more we learn, the more we realize how much we do not know, and the more questions arise. One of the deeper philosophical implications of Webb's discoveries is the recognition that the universe does not exist for our benefit or observation. It unfolds according to physical laws, indifferent to whether anyone is watching. Most of the universe is beyond the reach of observation, not because we lack the technology to see it, but because the fundamental structure of space-time places limits on what can be observed. Light travels at a finite speed, and space expands, and these facts together create a boundary, the cosmic horizon, beyond which no information can reach us. This boundary is not arbitrary or temporary. It is a fundamental feature of the universe, as real as the speed of light or the strength of gravity. There exist regions of space, galaxies, perhaps entire clusters and superclusters, that are so far away that their light will never reach us, no matter how long we wait. These regions are part of the same universe, governed by the same laws of physics, but they are forever inaccessible. They do not exist in some separate realm or parallel dimension. They're simply too far away, and space is expanding too fast for any signal from them to ever bridge the gap. This inaccessibility extends in both directions in time. Not only can we not observe regions beyond the cosmic horizon, but beings in those regions, if any exist, cannot observe us. To them, we lie beyond their horizon, in a part of the universe that is forever hidden. There is no universal now in the universe, no single moment that corresponds to the present everywhere. Instead, every observer has their own present, defined by the light and signals that can reach them, and different observers in different locations have different observable universes. This relativity of observation is a consequence of the finite speed of light and the expansion of space, and it means that the universe is not a single, unified whole from the standpoint of observation, but rather a collection of overlapping but distinct observable regions, each centered on a particular observer. This fragmentation of observability is not something that can be overcome by better technology or longer observation times. It is built into the structure of the universe. The implications of this are both humbling and isolating. Humanity, confined to Earth and its immediate surroundings, occupies a tiny region of space within the Milky Way, which itself is one galaxy among trillions in the observable universe, which itself is only a fraction of the entire universe. The vast majority of reality unfolds beyond our reach, in regions we cannot observe, influence, or visit. The galaxies Webb detects are already ancient, their light showing them as they were billions of years ago, and we have no way to know what they look like now. They may have merged with other galaxies, or dispersed, or changed beyond recognition, but any information about their current state will not reach us for billions of years, if ever. The universe we observe is a historical archive, not a real-time image, and the delay between event and observation increases with distance, until at the cosmic horizon, the delay becomes infinite and the signal never arrives. Yet within this vast, mostly inaccessible universe, Webb has given us a window into regions and epochs that were previously hidden. The early universe, once a realm of speculation and rough models, is now observable in unprecedented detail. Galaxies that formed when the universe was young are now visible, their light captured after journeys lasting billions of years. The structure of the cosmos, the web of galaxies and dark matter, is now mapped across immense distances. The nature of dark energy, dark matter, and supermassive black holes, while still mysterious, is now constrained by observations that were impossible a generation ago. Webb has not solved all the mysteries of the universe, but it has brought us closer to understanding the questions we need to ask, and it has revealed a universe more intricate, more surprising, and more vast than we imagined. The experience of observing the universe through Webb is, in a sense, an exercise in time travel. Each photon captured by Webb's detectors carries information from the past, and the deeper Webb looks, the further back it sees. The farthest galaxies observed by Webb existed when the universe was less than 5% of its current age, and their light has been traveling for over 95% of the age of the universe to reach us. These galaxies are among the oldest structures we can observe, and they represent the end of the cosmic dark ages, the moment when light returned to the universe after hundreds of millions of years of darkness. By studying these galaxies, we are witnessing the dawn of the universe's luminous era, the first steps in the long process of structure formation that eventually led to galaxies like the Milky Way, stars like the Sun, planets like Earth, and observers like us. The question of whether other observers exist elsewhere in the universe is one that Webb cannot answer directly, but its observations provide context. The universe is vast, filled with trillions of galaxies, each containing billions or hundreds of billions of stars, and many of those stars likely host planets. The sheer number of potential sites for life is staggering, and while we have no direct evidence of life beyond Earth, the conditions that allowed life to arise here, liquid water, stable environments, the presence of essential elements, are likely common elsewhere. Webb's ability to study the atmospheres of exoplanets, planets orbiting other stars, may eventually provide indirect evidence of life, if it exists, by detecting chemical signatures that are difficult to explain without biological processes. But even if Webb or other telescopes find such signatures, the distances involved mean that contact or communication is highly unlikely. The nearest stars are light years away, and most stars are thousands or millions of light years away. A signal sent to a distant star system would take thousands or millions of years to arrive, and a reply would take just as long to return. By the time a conversation could be held, civilizations would have risen and fallen, and the entire enterprise would be stretched across timescales far exceeding human lifespans or even the lifespan of human civilizations. This vast separation in space and time reinforces the sense of isolation. Even if the universe is teeming with life, most of it is beyond our reach, not only in terms of physical distance, but also in terms of communication and interaction. The observable universe may contain countless civilizations, each confined to their own small region of space, observing their own slice of the cosmos, unaware of each other's existence. Some of these civilizations may be far more advanced than humanity, with technologies we cannot imagine, but they are still bound by the same physical laws, the same limits on the speed of light and the expansion of space. No matter how advanced a civilization becomes, it cannot observe or influence regions beyond its cosmic horizon. The universe imposes the same boundaries on all observers, regardless of their capabilities. The acceleration of the universe's expansion, driven by dark energy, adds a poignant dimension to this isolation. Not only is most of the universe currently beyond our reach, but more of it is slipping away every moment. Galaxies that are currently observable are receding, and as space continues to expand, their light will become increasingly redshifted and faint until eventually it becomes undetectable. In billions of years, observers in the Milky Way, or an emerged remnant of the Milky Way in Andromeda, will look out and see a nearly empty sky. The cosmic web will have faded from view, and the universe will appear to consist of only the local group of galaxies, gravitationally bound together and isolated from the rest of the cosmos. These future observers, if they exist, will have no way to know that the universe was once filled with galaxies, no way to infer the existence of the cosmic web or the history of cosmic expansion. Their observations will be consistent with a small, static universe, and they will have no reason to believe otherwise, unless they discover records or theories left behind by earlier civilizations that observed the universe when it was still visible. This scenario, sometimes called the cosmic horizon problem, illustrates how the observable universe changes over time and how future observers will have access to less information than we do today. We are living in a relatively brief window, cosmically speaking, when the universe is observable in its full richness, when the cosmic web is visible and the expansion history can be inferred from observations of distant galaxies. Webb's mission and the broader effort of observational cosmology is thus not only a scientific endeavor, but also a kind of preservation. By observing the universe now, while it is still visible, we are creating a record of what exists, a map of the cosmos that can be passed on to future generations. This record will become increasingly valuable as the universe continues to expand and more of it slips beyond the horizon. In a sense, we are the witnesses to a universe that will never be fully observable again, and the data we collect now, the images captured by Webb and other telescopes, are a legacy that will outlast the visibility of the universe itself. The process of observation is also an act of connection. When Webb captures the light from a distant galaxy, it is receiving photons that have traveled for billions of years, carrying information about a galaxy that existed in the distant past. Those photons, once emitted by stars in that galaxy, have crossed most of the observable universe to reach us, and their arrival allows us to reconstruct the history of that galaxy, to understand its properties and its place in the cosmic web. This connection is fragile and fleeting. The photons that Webb captures are a tiny fraction of the total emitted by the galaxy, and most photons travel in other directions, never encountering any observer. But those that do arrive carry with them a kind of cosmic message, a record of the galaxy's existence, encoded in the wavelength, intensity, and spectrum of the light. By decoding this message, we learn about the galaxy, but we also participate in a process that links the distant past to the present, connecting an ancient galaxy to our current moment of observation. This sense of connection extends to the history of astronomy itself. For most of human history, the night sky was a source of wonder and speculation. Ancient astronomers tracked the motions of stars and planets, building models to explain what they saw, but they had no way to know what stars were made of, how far away they were, or how the universe as a whole was structured. It was only in the past few centuries, with the development of telescopes and spectroscopy, that these questions began to be answered. The realization that stars are distant suns, that galaxies are vast collections of stars, and that the universe is expanding are all relatively recent discoveries, products of the 20th century. Webb represents the latest step in this ongoing process of discovery, extending our view deeper into space and time than ever before, revealing details that were inaccessible to previous generations. But Webb also inherits the limitations of observation that have always constrained astronomy. No matter how powerful our telescopes, we cannot see beyond the cosmic horizon, cannot observe the universe as it is now at great distances, and cannot escape the constraints imposed by the speed of light and the expansion of space. The humility that comes from recognizing these limits is perhaps one of the most valuable lessons of modern cosmology. The universe is not designed to be comprehensible to us, and most of it will remain forever unknown. The observable universe, vast as it is, represents only a small fraction of the total, and the portion that we can study in detail is even smaller. Within this small, observable region, we have made extraordinary progress, mapping the distribution of galaxies, tracing the history of star formation, uncovering the role of dark matter and dark energy, and revealing the processes that shaped the early universe. But each answer raises new questions, and each new observation uncovers new layers of complexity. The universe is not a puzzle that can be fully solved, but an ongoing mystery, one that invites exploration and understanding but never provides final answers. Webb's observations of the early universe, of galaxies forming when the cosmos was young, of supermassive black holes growing in unexpected ways, of the cosmic web stretching across space, are all pieces of this larger mystery. They provide clues, constraints, and context, but they do not close the book on cosmic history. Instead, they open new chapters, inviting further investigation and deeper questioning. The galaxies that Webb reveals are not static objects, but dynamic systems, evolving over time, interacting with their environments, shaped by processes that span billions of years. Understanding these processes requires not only observation, but also theoretical modeling, simulation, and comparison across different epochs and environments. Webb provides the observations, but the work of interpretation and understanding is a collaborative effort, involving astronomers, physicists, and theorists around the world, each contributing their expertise to the collective effort to make sense of what we see. The images that Webb produces are not just scientific data, but also objects of beauty and contemplation. The deep field images, with their thousands of galaxies scattered across the frame, each at a different distance and a different moment in cosmic time, are visual representations of the universe's scale and complexity. They invite viewers to consider their place in the cosmos, to reflect on the vast distances and timescales involved, and to appreciate the fragility and contingency of existence. Each galaxy in the image is a world unto itself, containing billions of stars, perhaps countless planets, and who knows what else. And yet each galaxy is also part of a larger structure, a filament or cluster in the cosmic web, connected to others by gravity and by the shared history of cosmic evolution. The universe is both a collection of individuals and a unified whole, and understanding it requires holding both perspectives simultaneously. The experience of looking at these images, of contemplating the universe as revealed by Webb, can evoke a range of emotions. There is wonder at the sheer scale and beauty of the cosmos. There is humility at the recognition of how small and insignificant our own existence is in comparison. There is curiosity at the mysteries that remain unsolved and the questions that continue to arise. And there's perhaps a sense of melancholy at the realization that most of the universe is beyond our reach, that we're confined to a small bubble of observability, and that much of what exists will never be known to us. This melancholy is not despair, but rather a quiet acceptance of limits, an acknowledgement that the universe is larger than our capacity to comprehend it, and that there are boundaries to what can be known. Yet within those boundaries, there is still much to explore, much to learn, and much to appreciate. The observable universe, though only a fraction of the total, is immense, filled with galaxies, stars, and structures that we are only beginning to understand. Webb has opened a new window on this observable universe, revealing details that were hidden before. Its observations will continue to shape our understanding of the cosmos for years to come. The telescope is designed to operate for at least 10 years, and possibly longer. And during that time, it will observe thousands of targets, collecting data on everything from nearby exoplanets to the most distant galaxies. Each observation adds to the body of knowledge, refining our understanding of how the universe works, how it evolved, and what its future holds. The future of cosmology, in the decades and centuries ahead, will build on the foundation that Webb and other observatories have laid. New telescopes, more sensitive and more capable, will extend our view even further, detecting fainter objects, higher redshifts, and more distant epochs. But no matter how advanced these future instruments become, they will still be bound by the fundamental limits imposed by the speed of light and the expansion of space. The cosmic horizon will always exist, and most of the universe will always remain beyond it. This is not a failure of technology or a limitation that can be overcome, but a feature of the universe itself, a consequence of the laws of physics that govern its structure and evolution. In the end, the story that Webb tells is one of vastness, complexity, and inaccessibility. The universe is far larger than we once thought, filled with trillions of galaxies, each a beacon of light in the darkness. It is older than we once believed, with galaxies forming when the cosmos was only a few 100 million years old, and supermassive black holes growing to immense sizes in the earliest epochs. It is more structured than we imagined, with matter flowing along invisible filaments of dark matter, connecting galaxies and clusters in a vast cosmic web. And it is more dynamic, with processes of star formation, chemical enrichment, and galaxy evolution proceeding more rapidly and efficiently in the early universe than models predicted. But is also more distant, more isolated, and more unreachable than we might wish. Most of the universe lies beyond the cosmic horizon, existing but unobservable, forever hidden from view. Dark energy drives the expansion of space, accelerating it, stretching the distance between galaxies, and ensuring that, over time, more and more of the universe will slip beyond reach, fading from visibility as their light is redshifted into invisibility. This realization, that the universe is fundamentally unknowable in its entirety, that most of reality unfolds beyond the reach of observation, is perhaps the deepest and most unsettling insight that modern cosmology offers. It challenges the assumption that the universe is in principle comprehensible, that given enough time and effort, we can map and understand all that exists. Instead, it suggests that there are limits, boundaries imposed not by our technology or our intellect, but by the structure of space-time itself. We are observers confined to a particular location and a particular moment in cosmic history, and our view is necessarily limited by these constraints. What we see is not the universe as it is, but the universe as it appears from our vantage point, a perspective that is both unique and incomplete. Yet this perspective is not without value. Though limited, it is also extraordinary. We can observe galaxies billions of light years away, see them as they were in the distant past, and reconstruct their histories. We can map the cosmic web, trace the flow of matter through space, and understand how gravity shaped the large-scale structure of the universe. We can detect the signatures of dark matter and dark energy, infer their properties from their effects on galaxies and the expansion of space, and use this knowledge to predict the future evolution of the cosmos. We can study the first galaxies, the first stars, the first black holes, and understand how the universe transitioned from darkness to light. These are remarkable achievements, products of human curiosity, ingenuity, and perseverance, and they represent a deep connection between us and the cosmos, a connection forged through the photons that travel across space and time to reach our telescopes. The James Webb Space Telescope has not revealed the edge of the universe, because the universe, as far as we know, has no edge. It extends beyond the horizon, perhaps infinitely, continuing in all directions, filled with galaxies, stars, and perhaps other things we have not yet imagined. What Webb has revealed is the edge of what can be known, the boundary of the observable universe, the limit imposed by light speed and cosmic expansion. Beyond this boundary, the universe continues, indifferent to whether it is observed or understood. It exists, vast and unknowable, unfolding according to the laws of physics, a reality that persists whether or not anyone is watching. And within the observable universe, within the bubble of space and time that we can access, Webb has shown us a cosmos more rich, more complex, and more beautiful than we dare to hope. A universe that invites us to keep looking, keep questioning, and keep exploring, even as we acknowledge that most of it will forever remain beyond our reach.